All right, we are broadcasting. If there's anyone online, please send me a comment here to let me know that everything looks fine and that you can hear me. And if I can't see the comments coming up right here on my screen, so if one comes up and I don't notice it, let me know. A couple announcements before I get started. First one will be that we have an exam next week instead of a regular class. So we're not going to meet here. We're going to meet downstairs in the lab room right from the start. And it will go from the regular time, 5:05, until 7:50. Just some brief things about the exam, and I can answer more questions about it as well. It's going to be an open book exam. You'll be allowed to bring in any of your materials that you have. You can use anything that's on Blackboard, any notes, other textbooks, anything like that that you have. You can use software. The only thing really that you can't, you can even bring in your own computer, your own tablet, that's all fine with me. You just can't look stuff up on the internet while you're there. You should be self-contained while you're taking the exam, but with bringing in anything that you want. So it's a fairly liberal, notes type of thing, and basically just, don't want you communicating with other people during the exam. It will be not really a 2-hour, 45-minute exam. My hope is that you won't be pressed for time at all. Most likely, the fastest of you will be done in under an hour, and probably most of you will be done in under 2 hours, even if you're taking your time. I just don't want you to be under too much time pressure. It's going to cover these lectures 1 to 4, the assignments, and really anything that is in the lecture notes is definitely fair game, and anything that you've done in the labs or the assignments. So there's going to be components of it that are pretty conceptual, kind of following along the lines of the lectures, and then components that are just, do something in Excel or SPSS and give me the answer, maybe show your work. So so that'll be next Monday. I have, if you have a conflict, a couple of people I know have conflicts, let me know. I can arrange something else, but you have to let me know in advance, unless it's really an emergency. I'll post, if there's some interest here, I'll post some sort of sample questions just to give you a flavor for the exam. I should be able to post those by tomorrow. So yes. So the question was, with a decimal answer, how many decimal places should you record up to? I don't really grade on number of decimal places here. Like I think my suggestion would be just don't round off until the end, because if you round off in step 1 and then do some things, you could end up being off by quite a bit. But at the end, if you round to a correct number of significant digits based on the precision of the data that you got, it'll be fine. Or if you put in extra decimal places, it'll be fine. I'm not going to take off grades because of rounding at the end of. I mean, if you calculate a p-value of 0.3 and round it down to 0, then that's not going to work. But reasonable rounding, it's fine. And many of the questions, they are computer graded, but like on the exam and on the homeworks, like we review all of them so that because the computer is not perfect in how it does its grading. And if you see something where you rounded and it seems wrong, you can let me know and I'll review it. So the answer is, like, when it comes to computer graded stuff, I give a tolerance, and anywhere within this tolerance range, it'll be graded correctly. So as long as you haven't rounded off too early or done some kind of extreme rounding, it'll be fine. Yes? Sorry?
Everything's going to be on the computer. It won't be like on top of paper.
Right. The exam will be administered by computer. Yeah, it'll be on Blackboard. I'll have, you know, in case of dire problems with the computer, I'll have an alternative version available, but I don't know, that would be kind of a disaster if the power went out during the exam. I don't think you could take it. So hopefully we won't have any power outages, but it is a computer administered exam. Sorry? Yeah, yeah, you can bring scrap paper. That's totally fine. Calculator, whatever you want to have. I have in the past brought paper exams, but it is such a pain to transfer an exam out of Blackboard and into like Microsoft Word, and I inevitably end up with discrepancies between them. My preference is just to do it on Blackboard. Yep. No, you can use them on Blackboard. Yeah. Anything that's on Blackboard, you'll have full access to Blackboard during the exam. Yeah. You'll want to like open up a separate window probably so you can browse around in one window while you have the exam open. But yeah, Blackboard is totally fine. Any other questions about the exam? Yes. Oh, you can't see the questions anymore? Okay, yeah, we'll fix that. It's just a Blackboard setting that was unintentional. Okay. Great. Oh, one other announcement. The next class after the exam, it's a couple ahead. I've scheduled it on our YouTube station, and I'll change this in the syllabus as well. But I've been called for jury duty, which probably will prevent me from getting up to class here on time. One class late in October, so I'm going to record the lecture on the Sunday evening before. So you can attend it live online the night before or watch it the day of. And I'll try to find someone to come into class during the regular class time, and I'll try to get here as soon as I can that day as well to do other things other than just lecture to you during class. But I'm going to record it early because I'm going to be downtown. Yes. Yes. So on October 17th, we're going to have an R boot camp, and it'll be from 9 a.m. to 5 p.m. And I expect to send, I've just been waiting for the room number, but I'll send out an announcement this week with the details, including room number, or if we don't have the room number by Wednesday, I'll send the announcement anyways. Probably not, but the materials will be available. Like there will be notes and stuff from it. Yes. Sorry? October 17th is the date of our boot camp. It's a Saturday, all day Saturday. We'll order lunch. It'll just be an intensive workshop. And yeah, you don't need to learn R for this course. You're going to take BIOS 2, most of you with me, and you will need to know it for that. You can get around. I'm easygoing about software. You can avoid it still if you want to, but you should learn it eventually. It's good software to know. So this Saturday thing would be a great time to get an intensive introduction. Yeah. I'll have a registration for it. But I'm going to send it to this class and my other class first, so that as long as you register reasonably quickly, you'll get a spot. But just because, I don't know, we got a lot of people registering last time. It's cheap and basically just enough to cover lunch, so So sign up. I need to do the registration just so that I don't overfill the computer lab. But yeah. Yes.
Will it happen again?
Probably like in another year. Yeah. Yeah, I don't think I'll be able to do it before that, but I'd like to at least make it an annual thing. I'm actually going to be on a Fulbright fellowship from January through June of next year, so I couldn't do it at all in the first half of next year anyways. So, yes.
Is that mandatory or?
Is what? No.
Oh,
No, it's for people who want to learn R. It's not mandatory. Yeah. Yes.
Is it going to be like very basic class? Because I don't know anything about it.
It'll start from square one. So yeah, we'll start from the very basics and move rapidly all day long. It's, but yeah, it assumes no prior R knowledge. So, we fit a lot of material into one day, so some of it will get kind of confusing, but the idea is that you'll be up and started, you'll have the basics, and then you'll have more materials to to practice and learn more afterwards. It'll go from like the basics of loading in a file and adding and stuff like that, up to doing regression, plotting, and some more complicated stuff like that. Anything else? Okay, if you have any more questions about either those things, the boot camp or the exam at the end of class, you can ask then, and I'll stick around in the lab today as well. Okay. Oops. Okay, so I'm going to very briefly review a couple of the properties of probability from last class, and then introduce the normal distribution and the binomial distribution from your textbook in chapter 3. You'll recall the Venn diagrams, and we had Venn diagrams for mutually exclusive and non-exclusive events. These are two mutually exclusive events. I wonder how I can get rid of this silly thing. Yeah, how about that? The sound went out. Okay, it should be back now. Can you hear me now? I'm just going to check here. You all saw it. I had the sound turned on before. It was working. Okay.
Maybe whatever you clicked on, I should have.
So you click and get rid of. Okay, good. We're back in business. Okay. Oh yeah, that was probably that hiding thing that I did. It muted this microphone. Okay, I get it. And you're welcome, Amanda. Thank you. Okay, okay, yeah, everyone can hear. Good. Okay. Oh my goodness. I must say, Google Hangouts is probably the clunkiest Google app that there is out of all of them. Like, to start one of the Hangouts, you click on this page and you have to scroll down to about the 3rd page after a bunch of ads just to find the little button to do it. It's weird. Anyways, so I just put this up again because this really theoretical looking thing here, we're going to use it later in class today, and you will be using it lots. So in non-exclusive events, when there's overlap in the Venn diagram, for example, having cancer, having heart disease, something where it is possible to have both, then we use this intersect symbol to represent the intersection between those two events when both of them happens, the and. And then we had some slightly different rules in this case, and these you're going to use less in this class. You should know about them. But when it comes to using probability distributions for the purposes of inference tests, usually it's going to be exclusive events. It's going to be your null hypothesis and your alternative hypothesis. Those will be your two possible truths, and they're mutually exclusive. So these you should know, but I won't review them again in detail. Here again is all your probability notation. And I'm going to skip over those for the sake of time. So on to the new stuff. Any questions first about the probability notation stuff? Okay. So a random variable, I guess it sounds like either a simple thing or a complicated thing. But the way that we take it to mean in this class, it's anything where there is at least some uncertainty in it. So when we talk about having cancer or not having cancer, if it is after you've had the gold standard test and you know that is a realization of a random variable. If it's at some point where you don't know whether you have cancer or the disease or not, and you're about to get a test, then you can think of that as a random variable. And the case that we're usually going to take it in is talking about the probability of that event occurring over many people. And that will be our random variable. So, for example, the number of new cases of diabetes in New York City in a given year is a random variable. It's something that there's some finite probability in any given individual person, and summed up, that number is at least partly due to chance. There might be specific risk factors or things that contribute to it in a non-chance way, but there is at least an element of chance, so it's a random variable. Or the weight of a randomly selected individual in New York City is a random variable because you can pick anyone. Their weight could be anything within some range, and you could describe that probability of weights as a random variable. So we're not talking about one realization, we're talking about the unknown in the random variables. we actually covered some of these already, the types of variables, and without getting into it at the time, we were really talking about random variables, the categorical, the discrete, and the continuous random variables. All of those were things that you could measure, say, on an individual, and at that level, it's not random after you've measured it. But if you're talking about the aggregate distribution among many people, then it's a random variable. So just some notation, and this is also noted in your syllabus. We're going to use uppercase Roman letters for random variables, and we'll use lowercase for particular realizations of that variable. So if we're talking about the height of individuals, that might be an uppercase X, and if I were to then measure the height of everyone in this class, those would be lowercase x1, x2, x3 to indicate records or realizations of that random variable. So just a few examples here. Blood type, if we're talking about the blood types of everyone in this room, that's a random variable because I don't know what they are, but I could say something about the probabilities based on the probabilities that have been observed in large groups of people. So what kind of random variable is that? It's categorical, of course. Or the number of visits to the obstetrician's office during an uncomplicated pregnancy. What kind is that? Discrete, yep. Yeah, so you can think of this as, so these fractions of women are something that has been averaged over many, many women. The distribution of body mass index in a population. How about that one? Continuous, yep. Okay, so let's start with continuous random variables. We're going to describe the distribution of a continuous random variable by this thing that we call a probability distribution, or the probability density. And here's a couple examples. What they look like is we're going to have all the possible values of that variable on the x-axis, and then we're going to have a probability on the y-axis. So here's an example of commuting time in minutes. So if we were talking about how long it takes Hunter College students to commute to campus, this might be something that is based on collected commuting times from a survey from thousands of students. And based on that, for every possible value, or every possible value, it can't be less than 0. And I guess it could, in theory, be infinitely large, but it would taper down to 0 at some fairly large number of minutes. This describes the probability of that being someone's commuting time. So, it's got a peak here, in this case at about 15 minutes. This is probably, I don't know, at a campus that's not in New York. But the important thing is that you have a probability for every possible value, and more importantly is you can calculate a probability for any interval along this curve. So the probability of having a commute time of 45 minutes or greater can be calculated by this area underneath the right-hand tail. And for any interval like that, you can calculate an area, and that area will be a probability of interest. So it's not so much the actual values of this probability here that are going to be of interest, it's the area under intervals, and you're going to get lots of practice calculating those. Each of those intervals has a probability between 0 and 1. You can't have any probability less than 0, right? You can't have a probability greater than 1 either. It's got to be between 0 and 1. And the interval containing all possible values in the commuting time example from 0 to infinity is equal to 1. The total probability is equal to 1. These are the two probability distributions that are gonna do you good for most of this class. We will cover a couple other distributions that are important, but for now it's the normal distribution, the bell curve, and the binomial distribution for binary outcomes. The binomial distribution, and I'll tell you this again later, is a distribution that describes a so-called Bernoulli trial, but it's something where you have a number of independent events, each with the same probability. So the classic example of such a Bernoulli trial that is described by a binomial distribution is a coin flipped a certain number of times. So if you flip a coin 1,000 times, and that's one trial, and then you repeat that, or you have everyone in this room repeat that, flip their coin 1,000 times and plot the number of times that it comes up heads for each person who did it, that distribution that you plot is going to be a binomial distribution. So even though it's describing a binary variable, it's still a discrete, or if it's a large enough number of trials, a continuous distribution, if that makes sense. So what you need to know about the normal distribution. To start with, it's symmetric, it's bell-shaped. It's characterized by just two numbers, the mean and the standard deviation. If you know those two numbers, then you know everything about a particular normal distribution. It completely describes the distribution. And here's a few examples. Let's see, in red here, we've got mean 0, variance, standard deviation squared of 0.2. Then down here in green, the next one, also mean 0, variance of 1, so it's wider because the variance is larger. And down here, again, mean 0, variance of 5, so it's really wide. And then over here on the left, we've got a mean of -2, the peak's at -2, and a variance of 0.5. So somewhere between these two. Yes? It depends. It kind of is. Like when it comes to describing a normal distribution, it's pretty typical to describe the variance. I'm not sure why that is. But yeah, when you talk about distributions of a population, like something like this, it's pretty typical to use the variance. When we talk about sampling distributions, which won't be till after the exam, we'll usually talk about standard error, which is like a standard deviation. But both are totally typical and fine. So here's just a couple examples. The height of people tends to follow a normal distribution. And here's a not sure which population this is for. This is just hypothetical, but we have the mean height. This would be in inches. For women of 65 inches, I guess that would be 5'3" and a standard deviation of 3.5. And then for men, a mean of 70 and a standard deviation of 4. Those would stack up to each other kind of like this. So there's, the difference in means and then the difference in the standard deviations variance. So yeah, here's a question. Within what interval do almost all of men's heights fall? Probably between about 60 and 80, something like that. So that's 70, that's almost 3 standard deviations above and below the mean. And for women's, it's between about 55 and 75. So that's, again, about three standard deviations. And that's part of the empirical rule that I'm going to show you. The empirical rule. It applies to any normal distribution. And it's just, there's nothing like really deep or special about the empirical rule. It's just kind of a handy rule of thumb that can allow you to do some calculations easily and maybe in your head. And that is that for a random variable that's normally distributed, you'll have about 68% or 0.68 probability within 1 standard deviation of the mean, 0.95 or 95% within plus or minus 2 standard deviations, and 99.7% or 0.997 probability within 3 standard deviations above and below the mean. And you'll get, I don't know, it's a popular one for intro biostat because it allows you to answer a bunch of questions about probabilities from the normal distribution without having to be distracted by looking things up in a table. You can, questions that have to do with 1, 2, or 3 standard deviations of the mean, you can just do more easily using the empirical rule. But you could get by without the empirical rule. If you forgot about it, you could use the table like you're going to do for other ones. And we'll get to the table. So here's an example back from the height of women being 65 inches plus with a standard deviation of 3.5 inches. Does anyone want to tell me if we're talking about a sample or a population here? Yep. Very good. It's a population because we're using Greek letters. That's exactly right. I would use the X bar or something like that, and an S if this were estimated from a sample. So just from having that, we could estimate that about, if it's normally distributed, 68% of women would have a height between 61.5 and 68.5. So 65 plus or minus 3.5. And 95% within plus or minus 2 standard deviations, and 99.7 within plus or minus 3 standard deviations of the mean. This, by the way, is also can be kind of a handy way of, if you have some data, it's a rough estimate of whether it's normally distributed or not. If you have 100 data points or something like that, and you go calculate the mean and the standard deviation, if it's normally distributed, those data points, then they'll follow this empirical rule approximately. It's not a bad way to assess normality. So here's just an example of a slightly more complicated, still not too complicated, probability question what proportion of women are less than 68.5 inches tall? So 68.5 is the mean plus 1 standard deviation. And this would be, so this would be the area to the left of there. So you can answer this using the empirical rule. You know that there's 68% between -1 and +1 standard deviations. And since there's 68% here, there's 16% on each side outside of that. And we would just add 16 for the left-hand side. So 68 plus 16, that's what? 84%. So in this case, it might actually, this is maybe a little more complicated than using the table that we'll get up to, just because you have to add a couple things as opposed to getting the answer directly from the table. But it's still handy because you're getting used to the idea of intervals and breaking up your distribution into intervals and adding up probabilities. So actually, looking at this, you remember that rule about the exclusive events and the rule for the union of exclusive events? We're actually considering this problem as 3 exclusive events here. One being height below -1 standard deviation, another one height between -1 and 1, and another one height greater than 1 standard deviation above the mean. So we're splitting all possible heights into these 3 regions and taking advantage of the fact that because they're mutually exclusive and exhaustive events, probability, let's call this on the left A, B, and C, probability of A plus probability of B plus probability of C adds up to 1. So we've already been doing some kind of informal switching back and forth between heights in inches and number of standard deviations above or below the mean. Doing that, going towards standard deviations as a unit of measurement, is what we refer to as the z-score, or converting data into z-scores based on the assumption that it's from a normal distribution. So any variable that is normally distributed, you can convert it to this scale of the z-score just by subtracting the mean and dividing by the standard deviation. So in that case of the mean of 65 and the standard deviation of 3.5, by subtracting 6.5 and dividing by 3.5, we were converting into a number of standard deviations, or we were converting data to a z-score. Now when you convert a normally distributed variable to a z-score, when you plot it, normal distribution is a normal distribution. It looks the same. It's this bell curve. The only thing that changes is your x-axis. So whatever your x-axis was before, whether it was height or heart rate or whatever, after you convert it to the z-score, it will look like this, with centered at 0 and then almost all of your data between -3 and 3. This is actually probably not very accurate because -3 should be out somewhere further out here. This is called the standard normal distribution, because no matter what normal distribution you started with, after you do this transformation, it's the standard normal distribution. And they all look the same. They all are centered at 0 and will have 99.7% of the values between -3 and 3. They'll follow that empirical rule. And the biggest advantage to taking measurements and converting them to z-scores is that you can use the standard normal distribution for calculating probabilities. And the standard normal distribution, there are tables of. There's one in the back of your textbook. They're online. There you can pick out the one you like and you can use it. This is what the one in the back of your textbook looks like. It actually gives, it's a nice one because it gives both, it gives probabilities for negative values of z and positive values of z. A lot of tables of the standard normal distribution don't do that. They'll only give you one of them. Anyone want to hazard a guess as to why? Suppose you had a table that only gave you the area, the shaded area for negative z, and then didn't give you anything for the positive z's. What would you do? 1 minus. Yeah. Yeah, you could, if you wanted this probability, so let's say this is 2, you would have to look up the value for negative 2 and then go 1 minus that. And you'd get the same answer, but it's kind of, there's less room for making a mistake if you can just look it up directly. All right, so this is a screenshot from table B.1 of the Open Intro Stat textbook. Now let's use this table to find the probability that a normal random variable takes a value less than 1.43 standard deviations above the mean. So a z-score of 1.43 or less. So putting this in the context of women's heights, what would this mean? What probability would you be calculating here? So this is, the z-score, this is just math, but in terms of something concrete like women's heights, what would this question be asking? Yes? Yeah, it would be what's the proportion of women with a height less than 1.43 standard deviations above the mean, which would be 65 plus 3.5 times 1.43. So whatever that works out to, it would be what's the probability of having a randomly selected woman, or the proportion of women in a very large group of people who have a height of less than that amount. So since we have the positive z values here, we can just look this up directly. And the way you do it is you scan down the left to 1.4, and then you go, here's the 0.03. So you find where those meet. You get your first decimal place on the left column, and the second, or you get the first decimal place by going down the rows, and then the second decimal place by moving across. And we get 0.9236, and that's the answer. So if you take 65 inches plus 3.5 times 1.43, that's going to be, I don't know, about 70 inches or so. This is saying that 92.36% of women from that population will have a height less than that amount. And then conversely, the probability that the variable takes a value greater than that will be 1 minus this answer, 1 minus 0.9236, which is 0.07. So far, so good. Here's a few more important z values. The only one here actually that is really important, and probably you should commit to memory, not because you have to, but because you should just recognize it, is this one, the z value of 1.96, because it's going to come up over and over. And the reason it comes up is because we often talk about two-tailed significance levels of 0.05. So the probability under the normal distribution of having a value of z either greater than 1.96 or less than minus 1.6. Either one of those is 0.025, and when you add them up, it's 0.05. And so that's why this is a very important z value. You can use the norm.dist function in Excel. Actually, in R, there's something called qnorm, which basically makes any of these questions trivial to do. If you practice doing it a little bit, it's almost like cheating, just so you know. But yeah, it's easy also with norm.dist. You can just put in any z value or any probability and get the corresponding, either the quantile if it's a probability, or the probability if you put in a z value. So let's take that one step further quickly here and calculate the probability that a normal random variable falls between minus 1.43 and 1.43 above and below the mean. So before we calculated just the probability of something less than the 1.43, and that was like the 0.92, and the amount, the probability above being above 1.43 and got the 0.07. So these are two equivalent ways that you could think about that. The first one being calculate this probability, the 0.92, and then subtract this probability to the left. You get 0.84. Or you can calculate the area under these two tails, add them together, and subtract that from 1 and get the same answer either way. So it just depends on how you want to think about it. So I'm going to make this suggestion that when solving problems with the normal curve and with other distributions that we do, to actually go ahead and draw yourself a sketch of it and shade the area that you want. And this, I don't know, even though you have software that will calculate probabilities for you, this is a good idea to do, particularly when it comes to doing a one-tailed test, which we're going to show, or either because you are only interested in a one-sided alternative hypothesis, which we haven't covered yet, or because something is an inherently one-sided test. It lets you, pardon me, drawing this out lets you know what the probability is that you're calculating, and will help you to know that your answer is at least in the right ballpark. So, you can, by doing this, know that, if you get a value of a p-value of 0.99 when you're expecting a 0.01, you might figure out that there's something up. It's just a good way to be sure that you understand what you're doing. One way that you can use the z table is like we did. You want to look something up for a particular value of z, but you may also want to do it in reverse, which is you have a certain probability and you want to get the corresponding z value. You can do that with the table just by looking up the probability and reading backwards the row and the column to get the z value. And in software, it'll be called a quantile function. Like in R, it's the qnorm function. In Excel, it's what is it? It was, I think it's still norm.dist, but then there's an argument in it for getting a quantile. And that's, again, if you get that wrong, if you're calculating the quantile when you meant to calculate the probability, you might still get a value, but it would just be wrong. Of course, you would know if you put in a negative value, like z of -1, and tried to calculate a quantile, because it would be expecting you to provide a probability when calculating a quantile. So if you put in a negative value or something more than 1, you get an error. So just remember that calculating a quantile means you're going from a probability to a z-score. And when you're calculating a probability, it's the other way. You're going from the z-score to the probability. The z-score can be anything. The probability can only be between 0 and 1. So here's an example. What's the value of z for a cumulative probability of 0.025? We actually can figure this out from the empirical rule, because remember, 95% of the probability was between plus and minus. Well, it was 2, but more accurately, it's actually 1.96. The cumulative probability, or the quantile, the quantile for a probability of 0.025 is minus 1.96 on the z-scale, the standard normal distribution. Remember, quantile, the quantile for 0.025, that's the value for which 2.5% of the probability is less than that. Everyone recall the quantile from, I think that was our first class or our second class? The quantile being like the percentile when you're talking about, standardized exams. It's like, yeah, it's the probability or the total fraction of values that lie below that particular value. So for the standard normal distribution, minus 1.96 is the 0.025 quantile, or the 2.5 percentile. And 0 would be the 50th percentile. That's why when you enter a probability and want a z-score, it's called a quantile function. All right. So here's just, in case this helps, kind of a step-by-step set of instructions for calculating a probability for normally distributed random variables, which is you state the problem in terms of capital X, the random variable, and lower x, the realization. So, probability of capital X less than 67 centimeters or something like that. And you standardize x to restate this in terms of the z-score. So then it would be probability of z less than 1 or something if it was below 1 standard deviation. You draw your picture, shade it in, and then find that area using your probability function or table or the empirical rule. Okay, so the binomial distribution. I bring this up today because it turns out that it is related to the normal distribution, but we use it for a different purpose. So it's used for any event with 2 possible outcomes, that is a binary variable. And we use it to describe the number of one of those outcomes in a series of repeated independent events, like the 1,000 coin flips. So one event would be, say, does or does not have cancer, or heads or tails. We call that a trial. An example being here, what is the probability? So this is an example of something that you could describe using the binomial distribution. What is the probability that among 100 randomly selected individuals in New York City, 60 of them have private health insurance? So it could be, what's the probability that exactly 60 of them have private health insurance, or the probability that 60 or more of them, or 60 or fewer of them have private health insurance? What's the one other thing you would need to be able to answer this question? Yeah, the probability of an individual in the population having private health insurance. Exactly. So these are actually very important. Maybe you go ahead and circle these in your notes, because you need to know these. Having these handy will prevent you from using the binomial distribution in an inappropriate setting. You can only use it if these three things hold. First, the trial has two possible outcomes, which we will refer to as a success or a failure. A success won't always mean something good happening. It just means that that is what our probability is of. We might use a success to mean having cancer or something like that. It doesn't mean that it's a good thing. It just means that that is the outcome which we are describing the probability of. So two possible outcomes. Second one, that each trial has the same probability of success. That is, these are independent events. So in the example of the coin flip, every one of those coin flips must be independent. And in the example of cancer, these have to be people for whom the probability of one of them having cancer does not depend on whether others around them have cancer. Maybe a better example of where that would be violated would be an infectious disease. If you have a room full of people and one person gets the flu, then suddenly the probability of other people having the flu goes up. And that's not a Bernoulli trial, because those probabilities are not independent. Whereas if it's 30 people spread out on the remote corners of the world, maybe that would be described by a binomial distribution. That one's very important. By the time you're in BIOS 2, we'll cover methods for non-independent events that are counts. We use the Poisson distribution, the negative binomial distribution, other distributions besides the binomial distribution. So actually I already covered here the third one, that the trials are independent. The same probability of success, that just means that it's not that, I have a 10% chance, you have a 15% chance, you have a 20% chance. If that's the case, then you won't be able to use the binomial distribution. It's more complicated. All right. So if those things hold, then here is your probability of X successes in N trials. So successes being that the outcome of interest, the number of times that it has happened, so the number of people with diabetes or cancer, or the number of heads that you flipped, that's X in a certain number of N trials. So it's a bit of a cumbersome formula. Y'all remember the factorial? That's like 3 factorials, 3 times 2 times 1. But that's all you have to do. The only catch about this formula, you can program it into a spreadsheet and just use it, or you can use the binom.dist function in Excel. There's also the P binom and Q binom in R. The only catch is that once N becomes large, this starts becoming hard to calculate, because if you have 1,000 coin flips, 1,000 factorial is too big a number to calculate on any computer. Maybe not on any computer, probably on any of your computers or mine. But fortunately, there's an approximation that we can use. Here are a few examples. So remember the normal distribution was described completely by two numbers, the mean and the standard deviation. The binomial distribution is also described completely by two numbers, n and p. N being the number of trials and p being the probability of a success in each trial. So for n equals 20 and p equals 0.5, this is like flipping a coin 20 times and the number of heads. The mean here is 10. So the most expected number of successes is 10 out of 20. If we were to do 20 coin flips and count the number of heads and then have every one of you in this room repeat that, most of you, well, more frequently we would observe a 10. And then the next most frequently observed values would be 9 and 11, followed by 8 and 12, and it would fall off. For n equals 100 and probability of 0.5, that's 100 coin flips, and the mean number of successes is 50. And you'll notice that, that there's more spread. So when you have only 20 coin flips, the variability, I mean, it can only possibly go down to 0 or 20, so that it's not even possible to have a variation of more than 10 from the mean. But when we've got 100, you can have greater variation, and you see that the spread actually is greater. And then one more example here, with n equals 100, but a probability of 0.3. So say this is like a weighted coin that's less likely to come out heads. You see that the width of it looks kind of the same as this one where the probability of success was 0.5, but the mean is lower. Does anyone want to tell me if these distributions look familiar? What do they look like? Yeah, they do. They look like the normal distribution. And this is going to kind of come to the rescue when we're talking about large n. Here's just an example. I'm going to skip over this. To calculate the probability of 3 out of 4 individuals, so this is a small n being diabetic, you would want to use the binomial distribution, and you could just plug them into that formula and get a probability. If you wanted the probability of either 3 or 4 of them being diabetic, you could do it for 3 and 4 and then add those probabilities. All of these are now, I'm just taking advantage of that rule of summing of probabilities, summing to 1 if they're exhaustive. So the normal approximation of the binomial distribution. This is what you're going to want to use if you've got large n, because it's easier, and also because it's problematic calculating those factorials. This square root didn't quite come out right. This should extend over that whole thing. So that distribution, or that probability of the number of successes, has a mean of n times p, so the number of trials times the probability of success in each trial. So the 100 coin flips with a probability of 0.5, the mean is 50. And the standard deviation is this square root of n times p times 1 minus p. So remember, when the probability was at 0.5 and n decreased, then like we noticed in that plot, the standard deviation decreased. When n was fixed and p went down, it actually did change. It decreased again, although not quite as not as markedly. So here's an example of an application. If you have n equals 1,000 individuals, prevalence of diabetes equal to 0.1. So in this case, the number of trials is 1,000. A success, quote unquote, is having diabetes, and the probability of a success is 0.1. Then the mean is 1,000 times 0.1. The average number of people with diabetes out of a group of 1,000 will be 10. And the standard deviation of that, or if you wanted to calculate probabilities, like the probability of having between 8 and 12 people, you would use this standard deviation. It would be 1,000 times 0.1 times 0.99. And for large numbers, as long as both your expected number of successes and failures are at least 15, it's a very good approximation, this normal approximation. Even if they're less than 15, it's still not bad, but if it's above 15, it's a very accurate approximation. And so if you wanted the probability for 20 trials with a probability of success of 0.5, and you wanted the probability of observing a 5, 6, 7, or 8, using the binomial distribution, you would just calculate those 4 things and add them. If we're using the normal approximation, you would get your z-scores for 4.5 and 8.5 and calculate this area between those two values on your normal distribution after converting them to a z-score. All right, that's all we have for today. We covered normal binomial, some new notation, and as long as you're comfortable with, adding up probabilities from different parts of a distribution and looking up values in a table or calculating them with software and converting back and forth between the z-score and other scores, then you'll be fine for this unit. Any more questions about the exam or anything else before we head down to lab? Okay, thank you.